Hello everyone, my name is Abul Hassan and welcome to the video tutorial for Computer 3202. Today I'll be walking you through latent Dirichlet allocation, or one of the most influential algorithms in natural language processing and machine learning. Here is a core question that LDA solves. How can a computer automatically discovers hidden themes inside millions of unread documents? Think about that for a second. A hospital receives hundreds of thousands of notes a year. A company collects mountains of customer feedback. Nobody has the time to read all of that, but the themes inside of that are very valuable. LDA gives us a way to find those themes, and by the end of the video, you will understand how exactly it does that. What exactly is LDA? At its core, LDA is an unsupervised generative probabilistic model used for topic modeling. Let me break down those words for you. Latent. Latent means hidden topics. So you're not able to directly visible in the text what themes you're looking for. They have to be inferred from patterns in the words. Dirichlet. Dirichlet is a popular probability distribution model. Think of its way as generating probability distribution among themselves. We'll come back to this when we will be talking about hyperparameters. Now we come to allocation. Allocation means that every single word in every document gets assigned or allocated to one of the k hidden topics that we might be talking about. The big result at the bottom of all of this is for every document, it gives you a mixture of topics like this article is 60% about sports, 40% about finance. And for every topic, it gives you a probability distribution over words. For example, like this sports topic is mostly about ball, score, team, player who is winning, something like that. LDA has two main assumptions. Bag of words. What is bag of words? LDA completely ignores word order and grammar. It treats document like a bag of marbles. It only cares which words appear and how often, not where they appear. Even before they are given to the LDA model, there is some pre-processing which involves some tokenization, stop word removals and stemming before it receives the total word count for processing. Second thing is topic mixture model. So no document is forced to be exactly in one category, which is very realistic than hard clustering of the whole model. For example, a news article may be 60% politics and 40% economics simultaneously. Then the third that the inductive bias that LDA focuses on is Dirichlet sparsity prior. The Dirichlet sparsity prior biases the model in two ways. It assumes each document covers only a small number of topics, not all k equally, and that each topic is characterized by a small focused set of words, not the entire vocabulary. The whole design is theoretically grounded in De Finiti's theorem. If the words in a document are exchangeable, meaning their order doesn't matter for the probability model, they must arise from a mixture distribution. That's a mathematical justification for LDA's architecture. So let's look into how LDA thinks about a document. For example, we have M documents and we have to derive a topic distribution out of it. It LDA assumes we go through these three-step process, and step 2 and 3 are repeated for n number of words, which is the total number of words in those documents. Alpha is a hyperparameter. It controls the shape of the Dirichlet distribution we are about to sample from. Theta is the topic distribution for that document, which tells us what mixtures of topic does this document contain. Z is the topic assignment for each individual word. So if theta is 70% sports and 30% finance, we draw Z accordingly. Coming to W, it is the observed word. It is the only observed variable. We draw W from phi, the word distribution for that topic. Phi is defined separately. There is one phi for each one of the k topics, each sampled from the Dirichlet with parameter beta. Each phi tells us, given this topic, words are likely this. So the full generative process is beta shapes topic word distributions phi, alpha shapes document topic distributions, theta generates those topic assignments, z combined with phi generates the words w we observe. LDA then reverses this process to infer the hidden structure. We only see words in LDA, so LDA has to work backwards to identify the topics. It uses collapsed skip sampling, and here are the steps to it. Initialization, it assigns each and every word to a topic out of the K topics. Of course, it's a terrible randomization, but we are going to fix it. Second step, sampling. We temporarily believe that we don't know the topic assigned to each and every word. We remove from it. Now, step 3, reassigning. We apply the Gibbs sampling formula. The probability that word I belongs to topic K is proportional to two things multiplied together: the count of topic K in the current document times the count of this word under topic K globally, divided by the total words assigned to the topic K. This elegantly balances each local document preference with global word topic association. Then we keep on repeating steps 2 and 3 under a single theme or multiple themes come to appear. Each pass the assignment stabilize. After convergence, the word clusters that emerge from each topic are your discovered themes ready to interpret. Let's compare LDA with other ML approaches. LDA versus K-means clustering. K-means clustering offers hard clustering, however, LDA offers soft clustering, which is much more realistic and practical. LDA versus NMF. Both are fully unsupervised. However, LDA is probabilistic and NMF is algebraic, which leads to LDA producing much more better results for unseen data. Now the third one, LDA versus PLSI. Both have soft topic mixtures, but it has a critical flaw. It causes overfitting on large datasets. LDA fixes both the problems with Dirichlet prior. The key takeaway, LDA occupies a unique position, unsupervised like K-means and NMF, probabilistic like PLSI, but more principal and generalizable than all three. Let's discuss hyperparameters. LDA has three hyperparameters. K, the number of topics. It is the most critical parameter. If it's too few, topics are broad and they are merged. They are way too muddy. If it's too many, the topics get repetitive and they become redundant. Evaluation with perplexity is the tip. So you have to keep on trying new and new values depending on what suits the best for your document. Second, alpha. If it's less than one, each document focuses on a few topics, and if it's greater than one, it spreads across many topics. It is the Dirichlet prior over document topic distributions. Common tip is alpha should be equal to 50 divided by number of topics, which is k. Third is beta. Low beta topics are precise and specific. High beta topics use broader vocabulary. Common default by the research papers are 0.01. Limitations of LDA. Choosing K is non-trivial. K must be chosen in advance. Unlike non-parameter extensions, searching over many values of K is computationally expensive. Second, bag of words assumption. LDA cannot distinguish between any meaning that depends on word order or context. No automatic topic labels. LDA will produce a cluster of words. There is manual step limitations for full automation pipelines. Static. There is no temporal dynamics. So LDA will assume the entire corpus exists as a single point in time. Now let's walk through a sample application of LDA in real life. Imagine a catering company has 5,000 unread post-event feedback emails. No one has the time to read them all. What do? We take an input as a raw survey text. For example, dietary options were limited for our guests. Parking of the venue was a nightmare. We put it through LDA. We pre-process the text, tokenize them, and stem them. Then run LDA with K set to 3, alpha at 50 divided by K to keep documents focused, and beta at 0.01. And what do we discover automatically? We see 38% of the reviews were about dietary and food qualities, 34% staff and professionalism, 28% venue and logistics. Management can now see at a glance where to prioritize improvements without reading a single email. That is the power of LDA. Let's take a summary of what we learned today. First, LDA is an unsupervised probabilistic model that discovers hidden topics in text, that too without any labeled examples. Second, it models each document as a mixture of k topics, each topic as a probability distribution over vocabulary words. 3. Inference using collapse Gibbs sampling, iteratively reassigning words to topics using both document preference and global word topic counts until convergence. Fourth, three hyperparameters that we need to control the model. K for how many topics, alpha for how focused each document is on a few topics, and beta for how specific each topic's vocabulary is. Coming to the fifth point, what LDA enables is soft mixed membership clustering. Unlike k-means, a document can belong to multiple topics simultaneously, and unlike PLSI, LDA generates two unseen documents as well. Now coming to the sixth point, which are the limitations. Key limitations to are that K must be pre-specified, word order and semantics are ignored under bags of words. Topics require human labeling and the model is static. Extensions like dynamic topic modeling address that last point. The primary references are listed as follows, and that's all for today. Thank you for watching it, and see you in the next semester probably. Thank you.